Welcome everyone for this new SIPTA virtual seminar. So today we are very happy to receive Brian Hill, who will speak to us about confidence in belief in rational policy making. Okay, so now about Brian. So I did ask some people that know him very well to chair him, but unfortunately they were all very eager to do that, but unfortunately not today. But myself, I know Brian I know his work because I've been a fan of, let's say, French economists working with ambiguity, be it Jean-Marc Talon, Thibaut Gajdos, and also Brian, which is a core member of this community. And I remember a phone call from Brian one time a day asking me about a computation with p boxes. So I can say that I know him even a bit scientifically. So Brian he trained in mathematics, logic, philosophy, but now he works mainly in economics. He's both a senior researcher and a professor at HEC Paris, which is one of the biggest, let's say, business school in France. And he works both in decision under ambiguity with very formal contributions, dealing with axiomatization of decision under ambiguity in economy and aggregations of belief as well. But he also has very, let's say, applied work in the sense that he cares about how to make consumptions more ethical, or even how decision in economy can impact climate change. So it's a very, very broad area of research interest, some of them touching very, very closely to imprecise probabilities or being just, so to speak, imprecise probabilities, and others being of other nature.
Thank you for the invitation. It's a real pleasure to be here. I'm also a massive fan of the imprecise probabilities community. As you said, I kind of come from a slightly different, kind of belong to a slightly different community, at least first approximation. But I think there's kind of some really interesting synergies to be had between our two communities. So I'm very happy to present here and to get feedback, ideas, further thoughts, and so on and so forth. So this talk is going to be essentially a talk about rational decision-making and uncertainty representation. It's going to be a talk where the kind of end motivation is in helping policymakers deal with uncertainty in policy choices. That's going to be the kind of general final motivation, but it will be a talk kind of between economics and philosophy about uncertainty representation. So given the kind of policy motivation, let me just start with a type of policy choice. As Sebastian mentioned, I've got some work on climate policy, and there are tons of climate policy choices, right? Now, many of those choices, if you think, for instance, about choices of whether to build a particular type of infrastructure, the way these choices are made in many countries, the US as of today, but also France, the UK, and so on and so forth, is to do some sort of evaluation of all the costs and benefits, that's called cost-benefit analysis. And in those costs and benefits, they're going to look at the costs of the infrastructure in terms of future damages due to climate change, right? So if the infrastructure is going to lead to lots of CO2 emissions, that's going to lead to damages in terms of climate change, and they're going to try and take account of that. And the way they're going to take account of that is they're going to use a notion called the social cost of carbon, which you might have heard of. It's something which often appears in debates when you have economists talking about this. Now, social cost of carbon, how you set it is, in a sense, a policy choice. It's like an Uber policy choice. It's going to determine whether certain infrastructures are going to get built or not. Okay? And when you think about estimating the social cost of carbon, there are essentially two parts to that estimation. One is thinking about if you emit a certain amount of CO2, what temperature rise that's going to cause. The other one is thinking about what damages that temperature rise is going to cause to future economic activity and so on and so forth. Okay. Now, the second half is the economists' kind of favorite part. That's the part that they're supposed to be working on. I'm not going to talk about how much uncertainty there is there, I'm going to use as my example the climate science part where we're interested in the relationship between the CO2 emissions and the temperature rise, because that's the part we should know best. That's the part in which there should be least uncertainty. In fact, the essential unknown in that part is a constant, a little bit like the speed of light for climate change, called equilibrium climate sensitivity. It's roughly defined as a particular amount. If we put a particular amount of CO2 in the atmosphere, how much, and we let the climate come to an equilibrium, how much would the temperature change? Now, this is something that if there's anything in the climate sphere we should know something about, we should know something about this. The equilibrium climate sensitivity was the first estimate dates from the end of the 19th century due to Aaron House, who was the person who more or less discovered the possibility of global warming. And it's something which climate scientists spend an awful lot of time trying to estimate. So let's see what they say about it. And the place to look is the IPCC, or Intergovernmental Panel for Climate Change reports. So as you may or may not be aware, every 6 or 7 years, a huge collection of scientists come together to try and summarize scientific knowledge about anything to do with climate change. And one of the things they're summarizing knowledge about is the equilibrium climate sensitivity. In fact, one of the chapters in one of the reports is dedicated to this question. And if you open that chapter, this is what you're going to find in it. On the left, you basically see a summary of lots of basically all of the equilibrium climate sensitivity estimates we have today, right? What you see in different levels are the different methodologies, the different, if you want, subsections of climate science, which have been used to try and estimate equilibrium climate sensitivity. So just to give you an idea, process understanding are basically theoretical, what the theory says. Instrumental record is the data we have since we started measuring, say, 70 years ago or a little bit more. Paleoclimates are people who drill down into the Arctic or the Antarctic to try and work out what the climate, what the temperature was like and the CO2 was like kind of millions of years ago when the concentration was higher. Emergent constraints as a kind of new method of trying to put together process understanding instrumental record. What you see in blue at the bottom, those are simulation exercises. So we have completely different evidence bases coming from completely different directions, all trying to get the same thing. Equilibrium climate sensitivity. A huge amount of effort. And it's not that they're all giving estimates which are perfectly comparable. It's not like they're all using the same model, so we can do some kind of automatic statistical aggregation over these things. What the IPCC needs to do is it needs to kind of look at all of this evidence and try to come up with something to say about equilibrium climate sensitivity. And what it says, you can see on the right here. It gives the best estimate. The last report was the very first report in the 30-year history of the IPCC in which they gave a best estimate. And it basically gives these judgments when it says it's likely the ECS is in a particular range, ECS, equilibrium climate sensitivity, and it qualifies those judgments with a confidence interval. Now, in doing that, it's using a very particular language, the IPCC uncertainty language, which was codified about 15 years ago. So just to explain what that language means, when it says something is likely, it means that the probability lies in a particular interval. So likely means the probability is between 66 and 90%. Right? Very likely means it's greater than 90%. Right? So those are probability judgments. And then afterwards, it's going to use this confidence qualifier, which is basically supposed to tell you something about the amount of evidence or the type of evidence, or the quality of evidence, or the consistency of evidence behind this probability judgment, right? And the degree of agreement. So this is the introduction to my talk, because the talk is basically about if that is over around 130 years of climate science, that's what they can say on the easy part of a climate policy decision, right? The bit in which there should be least uncertainty. How can we take climate policy, and more generally, how should we decide in the face of uncertainty of this sort? Okay. Or this sort. And what I'm going to try and do in this talk is I'm going to kind of present and defend the proposal, and use that as a way to give an overview of issues to do with uncertainty representation, decision as they are relevant in the policy sphere. That's going to be the aim of it. So this is the plan. Essentially, I'm going to start from the standard story, which I'm guessing everyone knows. I'm going to set up a proposition, give a defense, come back to the climate policy examples very quickly. If I have time, but I think I won't, I was going to say something about aggregation, but don't hesitate to kind of write notes in the chat if you have any questions. So the standard story, I'm guessing everyone kind of knows it. So I'm just going to remind you of it and how it applies here. It's a position called Bayesianism. From the point of view of this talk, there are only two of its several tenets that we need. One is a tenet about how beliefs should be represented. Okay, and the idea is that they're represented by probability judgment. And here, remember that we have IPC scientists that are trying to turn all of this into this. So what they're effectively doing is giving their informed beliefs. Right? So when Bayesianism says something about belief representation, it's also saying something about uncertainty representation in any of these situations. So the first tenet is about uncertainty belief representation. And the second tenet is about decision, and it's basically the idea of maximization of expected utility. My guess is everyone's seen this sort of formula. The utility function is typically thought of as representing a person's desires or tastes. And you're supposed to take the expectation with respect to a probability measure, which is the one you get from tenet. It's worth reminding us why we're interested in Bayesianism here. I said that the social cost of carbon was used in cost-benefit analysis. The standard way that cost-benefit analysis is done is using expected utility. It's basically expected utility plus some other assumption, right? So it is the standard. And we're interested in it as a normative account of how decisions should be evaluated, deliberated, rationalized, and so on and so forth. Now, there are several reasons why it's so popular. Some of them doubtlessly sociological. I'm going to be interested in the conceptual reason. And very, very roughly, I think you can sort them into two barriers. There's going to be a whole bunch of reasons for defending Bayesianism, which are going to be based on its choice theoretical consequences, right? So here I have in mind things like Dutch book arguments or representation theorems. These are essentially results that show that certain properties of preferences or choice are equivalent to those preferences being represented as the maximization of expected utility for some probability utility function. And the idea, very, very roughly, and we're going to come back to this in a little bit more detail, the idea very, very roughly is if you think these properties of preference or choice are kind of normative, they are properties that you should be satisfying, and that's a good reason to choose by experience. The second sort of advantage of Bayesianism, which was mentioned several times in the philosophical literature, at least in the 50s and 60s, but relatively perhaps not emphasized enough today, is how clear, conceptually clear it is about the roles of different mental attitudes. So if you think about a policy decision, you're going to have experts in the domain, in the various domains where we need to know stuff about the world, right? So climate experts, for instance. And then we're going to have policymakers. And you would kind of like that the beliefs that we're using to take our group decision, they follow, or they are dictated by, or they at least respect the opinions of the people who know best, so set by experts, whereas the desires, the tastes, the values are those which represent those of society, so elected representatives and so on and so forth. Bayesianism allows that difference. The utility function represents the desires and tastes, so that's going to be in the policymaker's domain. The probability measure represents beliefs, that's going to be. And finally, just to finish off the kind of quick presentation of what Bayesianism is, just a reminder, it provides a framework for a whole bunch of other things like belief update, aggregation, uncertainty reporting, and so on and so forth. More than just the two tenets. Okay, so Bayesianism is a standard story. What does it say about the example that we started with? How should we decide in the face of that uncertainty, right? Basically, probability judgments which aren't precise, qualified by confidence. Well, here you have a quote from the British philosopher John Broome in his book on climate change. He was kind of one of the main philosophers in the IPCC several years. And what he basically says is the lack of firm probabilities is not a reason to give up on expected value theory, by which he means expected utility. Just stick with it and do your best with probabilities and values. Another way of saying the same thing, which is essentially what he's trying to say, if you aren't given probabilities, if climate sciences don't give you probabilities, then just pick a precise one and use that. Now, I'm guessing I'm talking a little bit to converted in this community, but that might strike you as a little bit ad hoc as a way of taking a climate policy decision or any policy decision. You could find people who choose different probabilities for no particular reason, and you can't really decide in their disagreement. Right? Difficult to tell which one is right. That's essentially kind of indicates the problem, the challenge that the source of uncertainty we started with, some people call it severe uncertainty or deep uncertainty. That indicates a challenge that poses for Bayesianism. To bring that challenge out a little bit more clearly, I'm going to move from concrete, kind of a real life example, to a slightly more idealized example, which I'm guessing several of you have seen. But I want to do it in a way that it's typically not presented, just to bring out what the challenge is to Bayesianism, because different people seem to see the challenges. Right? So you have a situation where you have two urns. This should hopefully ring some bells. Then I'm going to see if the bells are the same ones as I want to run. A situation where you have two urns. Both of these urns have 100 balls. Each of the balls is either red, black. In the unknown urn, one of the urns, you know nothing about the composition. In the other urn, you know that 50 of the balls are red and 50 of the balls are black. Now, this example, the first person I know who's discussed an example like this, though perhaps some people have discussed it before, is the American pragmatist philosopher Charles Sanders Peirce, back in the 1870s, 1880s. It was also discussed by John Maynard Keynes in his book on probability in the 1920s. Both of these people, with a little bit of interpretation, could be thought of as asking the question, what belief do you have about the color of the next ball drawn for each of the urns? And both of them make the point that whether you're thinking about the known urn or the unknown urn, if you're a Bayesian, the belief about the color of the next ball is going to be summarized by a single number, your subjective probability or your credence for that ball being red, say. And given the symmetry in the case of the known urn and the symmetry in the case of the unknown urn, that number has to basically be a half. So you have the same belief between the known urn and the unknown urn. Okay. But Peirce and Keynes point out, that seems to miss an epistemic difference, a difference in the amount of knowledge you have, and a difference in the amount of uncertainty there is between the known urn and the unknown. I'll use Keynes's way of expressing this difference. He says that the balance of evidence is the same between the two urns, but the weight of evidence is different. Right? In both cases, there's no particular reason, balance of evidence, no particular reason to think it's more likely for it to be red or black. But here you have a much stronger reason to think that there's no difference. You know much more in the case of the known. Now, perhaps some of you have heard of the notion of weight of evidence, because after Keynes's treatise of the 20s, there's been a whole cottage industry among Bayesian statisticians and trying to show that he was wrong in suggesting that Bayesianism cannot capture the notion of weight of evidence. And there's a whole bunch of suggestions as to how something like Keynes's weight of evidence can be captured with Bayesian machinery. Right? Some people, so one interpretation of Bayes factors, second order probabilities have been employed. I'm not going to go through the whole list, and frankly, I don't even know all of them. But weight of evidence is something. The suggestion that Bayesianism cannot capture something like the weight of evidence as a part of beliefs is a controversial suggestion. whatever you think about that suggestion, it doesn't really, whether Bayesianism can capture a notion of weight of evidence doesn't really help when we come to a second question we can ask about this example. Perhaps a question you've seen, question that's slightly more famous. It's Ellsberg's question about this example. He doesn't ask what you believe about the next ball draw. He asks which arm you would rather bet on. Okay, would you rather bet on the color of a ball coming from the unknown arm or from the known? And it kind of reformulated his observation is that no matter how Bayesianism can capture the notion of weight of evidence, when it comes to choosing between bets, there's only one number that counts for a Bayesian, and that's the probability of the next ball being red. So Bayesianism has to say you're indifferent between these two bets. By contrast, descriptively, normatively, doesn't seem unreasonable for people to prefer betting on the known arm. And you can even see a reason why they prefer betting on the known arm. It's because they feel that they know more about it. There is more evidence. The weight of evidence is high. This, I think, is the real challenge for Bayesianism and the one that's going to basically count for policymaking. Right? It's not a descriptive challenge. It's essentially a normative challenge. What this example is showing us, kind of putting together Peirce, Keynes, and Ellsberg, is showing us that whether or not Bayesianism can capture something like what Keynes was gesturing at with the notion of weight of evidence, it will deny it any role in choice. That's what's kind of, in a certain sense, controversial about the Bayesian position. It's saying that whatever epistemic the difference there is between these two arms plays no difference, should have no role in your choice about bets on the next color drawn. Now, that might sound a little bit too strong. That basically rules out using any of the confidence judgments from the IPCC. That rules out looking at how large the probability intervals are that the IPCC gives. That rules out any type of information that tells you how strongly certain belief probability judgments are held. Okay. So, hence this project. The project is basically trying to rebuild the whole Bayesian architecture, taking seriously the idea that something like weight of evidence has a role to play in rational decision. So the aim is going to be to provide normatively valid models for rational decision making under uncertainty and uncertainty representation. And then this is the kind of second part of the project, which I won't be able to talk too much about here, I think. Rebuild the rest of the frame. So there's going to be a paper about update, there'll be one about aggregation, there'll be one about uncertainty reporting, and so on. And how are we going to defend these models? We're going to defend them on precisely the desiderata that have been used to defend Bayesianism in the first place. We're going to defend them looking at their choice theoretical consequences, and we're going to defend them looking at what they can say about conceptual clarity, or how conceptually clear they are about the rules of mental attitude. Right? So those are the things that we're going to want from our account. Things we're going to want from our account. And of course, they can do better than Bayesianism on this weight of evidence, Ellsberg example. So that's going to be essentially good. So given that, let's kind of dive in. I'm going to start with the proposal, and then I'm going to go through the defense, and I'm going to try and use the defense to give you an overview of some issues that come up. So the proposal is going to be relatively simple. It's going to be based on a concept and an intuition. You more or less already guessed the concept from the title at the top. Right? So here's a citation from Peirce. The suggestion is that to represent a state of belief, you want to represent not only what he calls the inferred probability, but something about how strongly that probability judgment is held. One way of putting the same point is beyond the degree to which a subject endorses a particular proposition, which you can think of as something like the Bayesian probability, there's a degree to which the subject is confident in that endorsement. Or, to put it even more quickly, beyond one's beliefs, there's also one's confidence. And the idea is that one's confidence in one's beliefs is going to be part of the decision maker or an agent's epistemic state, or state of belief, or state of So what I'm going to need is a model of confidence in beliefs. I'm going to try and get to that model taking small steps. It's going to be, in a very precise sense, the simplest model of confidence beliefs that can capture confidence beliefs, as I hope I'm going to convince you in about 5 minutes. So let's start by looking at the initial Bayesian model. Okay? So as you are probably aware, as I've already said, Bayesianism represents beliefs by a single probability measure. The kind of screen here is supposed to be the space of a probability. As I'm sure you're well aware, a single probability measure corresponds to a complete consistent set of probability judgments. By probability judgments, I mean judgments about the probability of events. So the probability of A is no smaller than X, the probability of B is greater than Y. A and B are probabilistically independent. Each of these probability statements or probability judgments corresponds to a subset of the space of probability measures. That subset containing all those probability measures for which that judgment is true, right? So for instance, this is a probability judgment about red from the unknown arm. This is a probability judgment about red from the known arm. Since this single probability measure is in the set corresponding to both probability judgments, I'm representing the decision maker who holds both. Now, as we already said, we don't want Bayesian measure, so we're going to move to something a little bit more flexible, something that can hopefully capture confidence. And the first step would be to replace a single probability measure by a set of probability measures, which is very well known in this community. In economics, we call this multiple priors or sets of priors. In philosophy, and as far as I understand, in imprecise probability, the name credo sets is often used. This corresponds to a consistent set of probability judgments, but not necessarily a complete consistent set, right? So for instance, here we are. This is a probability judgment which is held everywhere in the set, okay? This is a probability judgment where the set neither says that the judgment, neither says that it accepts nor that it rejects that judgment. Some of the probability measures, for some of the probability measures in the set, it's true, for others, it's false. Now, we could try and interpret this in terms of confidence. We could say, this is representing someone who's confident about the statement with respect to the known arm, but unsure about the statement with respect to the unknown arm. But as a representation of confidence, that's a little bit too rudimentary. It's a little bit too rudimentary because it's representing confidence as something which is binary. Either the agent or the subject is entirely confident in something, or he's completely unsure. But in reality, confidence comes in degrees. You can be more or less confident in something. You can have more or less solid evidence for a particular probability judgment. We saw in the IPCC example, they can have high, medium, low, very high confidence. Okay? So we're going to want something that comes in. And clearly, the simplest thing up from this set of probability measures, which corresponds to a single consistent set of probability judgments, is to take a consistent set of probability judgments for each confidence level, right? Consistent set of probability judgments for high confidence, medium confidence, low confidence, whatever. Now, what does this correspond to in my space of probability measures? Well, each set of probability judgments is going to be a set of probability measures. So this corresponds to a nested family of sets of measures. The big sets in the family are those that correspond to high confidence, because if you ask for the judgments you hold with high confidence, there are going to be fewer judgments you hold with high confidence with respect to the judgments you hold with lower confidence. If there are fewer probability judgments you hold, that basically means that the corresponding set of probability measures is going to be bigger than the set of probability measures for low confidence. With this representation, we can therefore clearly say that whether you're more confident or not in some beliefs than others, right? So to hark back to the example we were using before, you can say that this is a representation of someone who's more confident in this probability judgment, it holds a high confidence set, than this probability judgment, which holds in a very low confidence set, only right in the middle. Notice also that even with respect to a given event, like red coming from the unknown arm, even though you have very low confidence in a precise judgment with respect to that event, if you ask for less precision, you can come to a judgment in which you have more confidence. For instance, here I have a judgment which is interval valued, asking whether probability is between 0.3 and 0.7. And here because there are more probability measures that satisfy that judgment, that's a judgment that can hold even with low confidence, so more than the previous judgment. So summarizing, what we have is a representation of confidence. It's the simplest representation you can imagine in a sense I'm going to say in a second. It represents confidence as a nested family of subsets of the probability space. Typically, you're going to take them to be closed, but if you don't want them to be closed, you don't have to. I'll call this thing a confidence ranking. If you don't like thinking about sets of probability measures, you can think about consistent sets of probability judgments. Of some interest in certain applications are going to be centered confidence rankings, which contain a singleton set. They're going to represent agents who are Bayesians with confidence. They can give a precise probability value to any event, precise value to any random variable, precise expectation to any random variable, but they may be more or less confident in some of those judgments. There are several properties to note about confidence ranking. Firstly, note that the model has a naturally very simple logic of confidence. Basically, it is a two-dimensional logic. It's got two parts. One is a kind of lifting part that tells you that if you have high confidence in a particular judgment, then you can deduce that you're going to hold the same judgment at lower levels of confidence, because lower level of confidence represent those judgments that you hold at that level or higher. That's pretty simple. Except that you can go backwards. So if you hold a judgment at low confidence, it doesn't necessarily mean you're going to hold high confidence. And the second part of logic of confidence is basically standard imprecise probabilities. It's the logic of Quetelet sets at a fixed confidence level. A second point about confidence ranking is that there's a confidence imprecision trade-off. We kind of saw that in the example of red and the unknown R. If you ask for more confidence, you can always say something about any event. It might just be that that thing is very imprecise. Worst probability interval is 0. If you want something more precise, you often can say something more precise, but you might have to accept you're going to have lower levels of confidence. When you actually talk about how experts report, one of the trade-offs they have to make between what's sometimes called accuracy and informativeness, they want to say something which is informative. This makes this trade-off very, very precise. You can be more informative in the sense of being more precise, but you're going to be less informative in the sense you're saying something with less confidence, which has less evidence. And vice versa. If you want something with more evidence, you might have to accept less precision. And that's just a fact about the amount of evidence we have and what we know. Okay. There are equivalent representations of this. We probably don't need to go into that. If you want, instead of using subsets of the set of probability subsets of the space of probability measures, you can use other things, belief functions, or whatever that you normally use. One other note about this that is going to be important for the next move is that this is entirely ordinal at the second order level. No numbers are being put on confidence levels. No numbers with any meaning, at least, are being put on confidence levels. This means that this representation of confidence is, this gives it an advantage for certain, this gives it an advantage in terms of tractability when, for instance, you're trying to elicit confidence levels, or you're trying to map something like the IPCC uncertainty line, which was talked about high, low, only ordinal levels of confidence. It counts as a disadvantage when you come and talk about decision. The less structure you have in your representation of uncertainty, the more work you're going to have to do to come up with a decision. So let's talk about the next. So the proposal is going to have two parts. One is concept, confidence. And the second part is going to be an idea about how we should take decisions with confidence. What role confidence in beliefs does or should play in decisions. So we have citations from people. This is Frank Knight saying that it should play a role. The question is what role? So to kind of introduce the intuition that I'm going to be working with, on which we're going to be building account of decision, on which we're going to be building the confidence framework, essentially, I'd like you to consider and compare two situations, right? So let's hark back to the climate policy example we had at the beginning, where the IPCC gave a best estimate kind of a best hunch estimate for this equilibrium climate sensitivity, and then more details in terms of probability and confidence. And I'd like you to think about how comfortable you would be with climate change policy that could impact billions of people today and in the future being made on the basis of the best hunch estimate of the IPCC. And I'd like you to compare that to how comfortable you would be with climate scientists after their conference in the bar, betting, taking wagers about what the equilibrium climate sensitivity value is on the basis of their best hunch estimate. So I don't know, Alice and Bob entering into a wager on the basis of their best hunch estimates about what the ECS values are. If you're anything like me, or a few other people who have seen presentations like this, you might have the feeling that you would like climate change policy that's important and can impact billions of people to be ideally based on the most solid beliefs, and that you'd be uncomfortable about them being made just on the basis of best hunches. Whereas there doesn't seem to be anything particularly wrong with flippant decisions like small wagers between individual people being wagers, say, for small monetary amounts or for a beer or for a meal, being based on similarly best hunches. If you have that intuition, then it would seem that you are kind of implicitly subscribing to a maxim a little bit like before. Higher the stakes involved in the decision, the more confidence is required in a belief for it to play a role in that decision. So it's a maxim which basically gives a role to confidence, and that role is to regulate which beliefs qualify for playing a role in the decision. And it's going to regulate it in such a way that we're going to be asking for high confidence beliefs. We're going to have beliefs with a better pedigree in a certain sense, benefiting from more evidence, larger amount, better quality, more consistent evidence, if the decision is more important. So confidence has a role in regulating which beliefs qualify for playing a role in the decision. So that's the intuition. Said the approach is going to be based on concept and intuition. This is intuition. The rest of these few slides are going to be turning that intuition into a framework for decision making. And I'm going to do so by basically just brute force formalizing it. So what does it ask me to do? It asks me to assign to each decision a level of confidence deemed appropriate for the decision. The level of confidence which would be required of beliefs for them to play a role in that decision. Well, levels of confidence we've already seen, they correspond to families of my nested family sets. So what I really need is an assignment for each decision or each option of an assignment for each decision to a confidence level in my nested family sets. And the function that I'm going to take to do that assignment, the only thing it really needs to satisfy, the main thing it needs to satisfy to capture this maxim, is a sort of monotonicity, right? It needs to make sure that it's going to take high stakes decisions, higher confidence levels than lower stakes decisions. Okay? I'm going to call a function that does that, or a function that does that, a cautiousness coefficient. And don't worry, we're going to be talking about what that cautiousness coefficient is a little bit later on in this talk. Bear with me and assume that we. Now, once we introduce this map from decisions with their importance into confidence level, we basically get for free a decision framework, right? A family of decision models, if you want. Right? Each element in the family is going to have three ingredients: a utility function, just like a standard Bayesian story, confidence ranking, which is my representation of beliefs and confidence in beliefs, and this cautiousness coefficient, like I introduced in the previous slide, which picks out the appropriate confidence level for the decision in hand. And once you specify a decision rule, then you basically get preferences or choices or whatever you want to call them out for free by using these ingredients, right? So preferences concerning a particular function, a particular act, F, a particular option, whatever you want to call it, are going to be a function of the utility values that act gives. The set of priors, which is picked out by your cautiousness coefficient, are according to some decision rule that you set up. And there are several decision rules on the market, so to speak, that are going to give you preferences when you feed in this and a set of priors. Just to give you some examples, again, in the economic literature, this is relatively well known. I'm not sure how much it's discussed in other literatures. So one example is the unanimity rule, the first one on the list. Basically, preferences are such that you prefer one option to another if and only if the former option has a higher expected utility for the latter one. All probability measures in the set. So, I think that one's fairly often used in imprecise probability literature. There's the max min expected utility rule that looks at the worst case expected utility over a bunch of options. And then there are kind of other versions. This rule looks at a mix of the worst case and the best case, and so on. Okay, just to see what these things look like, let's just walk through what this sort of decision rule would look like on a particular case. I'm just going to look at the maximum expected utility decision rule version. Okay? So what is it going to do? It chooses the option to maximize this, the worst case expected utility, over a set where this set is going to depend on the option which is being evaluated. The idea being that options involving higher states are going to be set to larger sets, but you're going to require more. Just as an aside, again, talking across literatures, it's relatively well known that if you were using as your kind of, instead of a set of priors, you were using a belief function, then that belief function is essentially what's often called in the appropriate part of analysis a convex capacity. The only decision rule satisfying a monotonicity property and that takes convex capacity as its input to something called Schottky expected utility, introduced by David Schmeider in the 80s. Basically, the Schottky integral. And on convex capacity, Schottky expected utility is equivalent to maximum expected utility over a set of probability measures called core, which is basically the set of probability measures that dominates belief. So this would be the decision rule you would use if you wanted to use belief functions and you accepted the idea that perhaps different belief functions are relevant in different contexts. Okay, close that parenthesis. So what does this rule say? Basically says, if the stakes are high, this set's going to be relatively larger. So the set of expectations is going to be relatively larger as well. If you're very confident in the appropriate beliefs, the beliefs you need for this decision, that set's not going to be too large and you're not going to be too pessimistic. If you are not very confident in your beliefs, that set is going to be larger and you're going to be more pessimistic. So the minimum here is going to give you pessimistic behavior, but the pessimism is going to be regulated by one's confidence and the importance of a decision to be taken. The more confident you are in the appropriate beliefs, but the lower the stakes required, the less pessimistic this decision. Another way of putting it, it can be argued that this decision rule captures a kind of the following simple advice: choose boldly if one has sufficient confidence for the decision at hand, choose cautiously if not. And I would argue, or have argued, that there are very few non-expected utility rules correspond so closely to maxims of this sort. And in particular, for people who have followed the discussion on the maximum expected utility rule, it's typically considered to be extreme. This shows that once you put confidence in, you're gonna resolve some of those extremity problems because you're not going to be using big sets for very low stakes decisions. You're going to be using smaller sets. Finally, since the maximum expected utility rule can capture the Ellsberg behavior that we started off with, so preference for choosing the better than the known, so can confidence. Right. So that's the account. I'm just going to say one or two things about its defense. And I'm going to try and basically go through the two desiderata we put back. Okay. The third one was to deal with severe uncertainty situations, but the point of this example was to show that it can. So the first one is the acceptability of choice theoretical consequences. This is a big literature. Typically, what you would do is you would take a given decision rule, you would prove some representation theorems, and then you would examine the axioms in those representation theorems and see what's being violated by this confidence approach that, for instance, is not violated by the standard Bayesian approach or by other approaches. That's been done. It's a little bit technical as a discussion, so I'm not going to present the discussion in those terms, because no matter which model you take, you're always going to come to the same sorts of conclusions. It's going to be the same sorts of properties which are going to be on the table. So I'm going to try and give an idea of those properties by looking by doing it on the case of Dutch books, which hopefully we're more familiar and perhaps might talk to this community a little bit. Just as an aside, there are a bunch of dynamic choice theoretic arguments for expected utility, in particular against violations of the sure thing principle. They affect any account of decision that tries to violate the sure thing principle, and in particular all other accounts that try and move away from expected utility. I'm not going to consider those sorts of arguments here. If you want, you can see another work of mine for a rebuttal for those arguments. I don't consider them to cause a problem to this confidence approach for reasons that I set out now. So that said, let's try and give the idea in the case of Dutch books. So a standard Dutch book argument, as you typically find in the often in kind of the philosophy literature, looks a little bit, the classic version looks a little bit like this. You're gonna have some conditions on bets. The most famous one is Dutch book invulnerability. The fact that you are buying and selling behavior. I can't put some of your purchases and potential sales of bets together and come up with a sure loss for you. Right? That's Dutch book invulnerability. I can't do that. They're equivalent to those bets being driven by probabilities in the sense that you're betting quotients of probability. The sort of literature talks about bets on events, A, with stakes, S. It's an event that gives you S euros if A happens. And they're basically interested in betting quotients, which are the ratio value of the stakes that you're willing to buy and sell the bet. Right? We can say similar things in terms in the language of provisions, right? So in provision language, you're not going to have bets in event A, you're going to have more generally random variables over a space. But you can still associate to those random variables stakes. For instance, kind of in parallel with what's going on here, I could take the stakes to be the maximum absolute outcome of the random variable. And similarly, when you're interested in betting quotients, the equivalent here is to look at the lower provision, which is going to give you the maximum buying price, and normalize it by the stakes. So that's the standard Dutch book argument. As guessing everyone is well aware, it relies on some assumptions, the first one of which is very well known here. It assumes that the price at which there is a price at which you're indifferent between buying and selling a bit. Right? In the language of lower provisions that you see at the bottom of the screen, that's basically a self-conjugacy property. It's sometimes called buy-sell coincidence. It basically says you can't have any pursuit. Now, I'm not going to argue against this assumption. I think this literature has done a great job at telling us why we don't necessarily have to buy it. And we also know what happens when we drop it, right? We can drop this assumption. We can have a maximum buying price. It's different from the minimum selling price. We can have provisions that don't satisfy self-conjugacy. And we know that we can replace our Bayesian conditions with other conditions on bets, and they're going to give us that the buying and selling prices aren't precise probabilities. They're the maximum minimum probabilities of a fixed set of prices. So we basically get to an imprecise probability style representation. Notice that we don't, as is well known, just a reminder, we don't sacrifice Dutch book invulnerability here. This maximum minimum probabilities of fixed set of priors still is going to satisfy Dutch book invulnerability. Okay, and the conditions here are going to be the standard conditions for coherent lower provisions. So that's something that the confidence story will also have to weaken. It's going to follow imprecise probabilities in weakening the assumption that leads to a precise probability as opposed to some kind of fixed set. But there's another assumption in the Bayesian story, which is retained by single sets of priors or multiple priors or creedal sets. And that's the assumption that the betting quotient is independent of the stakes. Okay? Because it's independent of the stakes, I'm going to call this assumption stakes independence. I've put it in terms of provision language here. What does it say? It says if I take my random variable and I renormalize it such we've got stakes S, and then I take its lower provision and renormalize that, so I'm considering the lower provision as a ratio of its betting quotient, then it doesn't make any difference whether I take S or T, it's going to be the same for all stakes. Right? In a certain sense, the buying price and the selling price as a ratio of the stakes is independent of the stakes I'm using. Or another way of saying the same thing, if I'm willing to buy a bet on a particular event, think ECS, equilibrium climate sensitivity, just to hark back to the example before. If I'm willing to buy that bet when what I have at stake is $10 or 10 euros, then I'm also willing to buy that bet if what I have at stake is 1,000,000 times the utility value of 10 euros or 1,000,000,000 times the utility value of 10 euros. Bumping up the stakes doesn't change, in a certain sense, my propensity to bet. But given the example that we started with and the intuition we were playing with, that sounds like a little bit of a strong, a strong requirement. It doesn't seem to be a requirement of rationality. It seems to be reasonable for you to be willing to buy at a particular price when the stakes are small, but being much less willing to buy at that price when the stakes are large, perhaps because you don't want to rest important decisions on beliefs in which you don't really particularly have much confidence on bet your best hunch beliefs. That would suggest that we shouldn't be imposing stakes independence. We should be imposing a property that I call stakes dependence, something that says something about betting odds and how they change with the stakes, but only imposes a structure in one direction. It would seem reasonable that if you chose to buy the bet when the stakes were high, 1,000,000,000 times the utility of 10 euros, then you should be prepared to buy the bet at the same betting quotient when stakes are low, only 10 euros. But it doesn't, as we saw in the example, it doesn't mean you have to have the implication going the other way. That would suggest that you have this type of stakes dependence problem. For lower stakes, your betting or your highest betting buying price can be higher. Your best buying price can be higher, right? So if you're willing to buy it at high stakes, you're definitely willing to buy it at low stakes. Now, if you take the standard size probability story and you replace stakes independence with the stakes dependence, then more or less the same sorts of conditions on bets are going to give you buying and selling prices, which are maximum and minimum probabilities, not of a single creedal set, but of a confidence rank. So a nested family of sets. Where there are higher stakes, those sets are going to be higher, the maximum minimum probabilities are going to be farther away. When there are smaller stakes, the sets are going to be lower, they're going to be closer. Okay? And these conditions on bets, they are basically going to imply Dutch-book invulnerability. So in the same way that there's no Dutch-book invulnerability problem with imprecise probabilities, there's going to be no Dutch-book invulnerability problems with a confidence ranking story. Now, again, I'm not quite sure. I'm not quite sure kind of what's standardly known or accepted in this community, but I might just stop for a second and make the same point about stakes independence precisely in the language of provisions. Okay, so often the imprecise probability community, or some bits of it, seem to work with coherent law provisions. If you read appendices of economic decision theory papers over the last 30 or 40 years, you're going to find something which is essentially coherent law provisions in the middle of their proofs. And for quite some time, they've basically identified two properties of these provisions which play quite a big role. Right? They are properties of coherent law provisions. One of them is called constant additivity. It basically says that if you add constant amount to your random variable, then that's basically you're going to shift your coherent law provision by that constant amount. And positive homogeneity, this one is much better known in this literature. It basically says you're going to multiply by. Now, in the economic literature, it's been recognized that these correspond to assumptions about people's uncertainty aversion, right? About people's uncertainty attitudes. So the analogy is something like this. Back in the 60s and 70s, economists who were interested in decision under risk asked themselves the question, if someone is given a risky prospect and we're interested in how much they're willing to pay for that risky prospect, which indicates something about their risk attitudes, how is that amount they're willing to pay, how is that affected if their background wealth moves up and down? Okay. And you can ask that question in two ways. You can ask it where the risky prospect stays the same when the background wealth moves up and down. That's sometimes called absolute risk aversion. Or you can ask that question where the risky prospect stays the same relatively to the background. So if the background wealth increases by a factor of 100, then the risky prospect is going to be spread out by a factor of 100 to stay the same relative to the background. That's sometimes called relative risk aversion. These two properties have been recognized as corresponding to the similar things in the case of ambiguity aversion. Right? It's pretty easy to see in this case. You can think of this C as your background wealth. It's basically saying something like, if you move that up and down, then your attitude, how you're going to evaluate this prospect, how you're going to evaluate that uncertainty, is going to be unaffected. It's going to be insensitive. Wealth, which is sometimes called constant absolute. This says something similar in relative terms. It basically says how you're evaluating it is going to be indifferent to how it situates in relative terms. Right? If I explode it up or move it down, that's not going to change my evaluation of things. Yeah. Now, fun fact about constant absolute and relative uncertainty aversion: neither have been shown. It's been shown that neither hold descriptively, even though there are quite a lot of economic models that satisfy it. And more importantly, I've never seen any normative justification for either of them. Certainly in the economic literature or the philosophy literature that I'm aware of, no one's ever tried to justify the normative. And in fact, our confidence decision maxim provides a justification for potential violations of both. Because if you have a particularly risky prospect, but that prospect is in the background of you having a huge wealth, then it becomes a small stakes decision. And you can just take it on the basis of a hunch. You can take it flippantly. Similarly, if you take a small decision and you explode the consequences by multiplying them up in utility space by a huge amount, then it becomes a big stakes decision. And the confidence maximum would say you have to be, you might require more confidence in beliefs, and therefore you're allowing yourself to use fewer beliefs to evaluate that decision. Okay, so the general moral is to get to the confidence rule, you're not violating anything like monotonicity or Dutch book and vulnerability. You're taking two steps. One is a step you take with imprecise probabilities. Another one is a kind of further step you take to the confidence rule, which is basically about this question of whether stakes independence is a rationality constraint. And I've suggested it's not. If it's not, then there seems to be no reason to think that there are unacceptable choice theoretical consequences to the confidence. Let me just take a little bit, another few minutes to say something about the roles of different mental attitudes. Again, this is a debate about that. I'm not quite sure how well it's known outside the economic decision theory community. So let me give you a take on that debate using a simple example, this maximum expected utility that I started with before. Now, there are two elements of this model. One is the utility function. The other one's a set of priors, what many people in the imprecise probability literature call Creel sets. The utility function could be thought of as representing or reflecting decisions over outcomes. The set of priors can be thought of as a reflection of beliefs. That's what people originally think when they see this sort of model. But we can test that interpretation by taking a preference-based or behaviorally defined notion of attitude to uncertainty. Right? So again, there's an analogy with the literature on risk, where we've defined, where in the 60s, people defined what it meant for one decision maker to be more risk averse than another. But this is the same definition, but in the case of uncertainty, it says that one decision maker is more averse to uncertainty than another if whenever the first decision maker prefers an uncertain option, over one that is not uncertain, so that's what this means to say a constant uncertain option or one that's not uncertain, then the second decision maker also has that preference. If that's the case, the first decision maker must be more averse to uncertainty, because there could be cases where he prefers uncertain X to non-uncertain X, whereas he does. This is clearly not a complete ranking, but it is something that, I mean, it's kind of like a minimum ranking of then you can ask what that corresponds to in terms of models. And it's shown more than 20 years ago that if you have a decision maker that's more averse to uncertainty and he's using the maximum expected utility model, then that basically means that his set of priors is larger in the sense that it contains a set of priors about the decision. But there's an issue here, right? Because this is supposed to be an issue of tastes, whereas our original idea was the set of priors was supposed to capture in one way or another beliefs. So what's going on here? Well, one way of seeing it is to just take a simple example. Right? So imagine you've got one policymaker whose sets of priors contains a set of priors of the other policymaker. Why is this policymaker's sets of priors smaller? There can be two answers to that question. It could be that that policymaker has more information or beliefs, or it could be that he's got the same information as beliefs, essentially the same set of priors, but because he doesn't want to be too cautious, he's going to allow himself to reduce that set of priors when he chooses according to the maximum expected utility model, something which is allowed. Now, the point here is, if you're interested, if you kind of take the point of view of the behavioral point of view, where you're looking point of view of the model, the maximum expected utility model cannot distinguish between these two possibilities. Right? So it can't, not only can it not answer the question, is this difference epistemic due to beliefs, or a value difference due to caution? It can't even properly represent the possibility. So it's definitely not separating beliefs and desires. Right? There's a kind of value element and a belief element and an epistemic element mixed up there. Let's see how things go in the confidence model. Right? So here we have a model with several elements. Utility function can be taken as desires over outcomes. As before, confidence rank is supposed to be a representation of belief. What does the confidence coefficient do? It's the function that assigns to each decision the appropriate level of confidence demanded of belief for them to play a role in that decision. Okay? So in a certain sense, if people differ in the confidence coefficient, it's as if they're asking for more or less confidence in the face of decisions of a given input. So the confidence coefficient at first glance looks like it captures something like attitude to choosing on the basis of limited confidence, which I'm going to suggest is an uncertainty attitude. And you can check that using the sorts of results I just, using the sorts of notions I put in the previous slide, right? So you can take precisely that same definition of attitude to uncertainty, and you can show that it corresponds precisely to the differences in the confidence coefficient for people who have the same utility input, right? So differences in uncertainty and aversion come down to using different sets in your nested family set. A person who is more averse to uncertainty is always going to demand more confidence. You can do this with one decision model. You can do it with another decision model. The conclusion is always the same. Right? So conclusion: there is a clean separation between beliefs and desires, where the desires are going to give two types, right? Attitudes to outcomes, and something of the order of uncertainty, attitude to choosing in the absence. And that kind of rests most of the case, right? We've seen that there are no particularly unacceptable choice theoretical consequences. The only axiom violation is basically a direct consequence of the central intuition behind the proposal, which didn't seem unreasonable. And we do have a neat separation of beliefs and taste, and it can deal with some severe uncertainty situations. And moreover, it has an ordinal notion of confidence, which is sometimes useful. And as I say, it's the only model that can be used. Can I just check how much time I have left?
You're about, I guess it's mostly 1 hour since you started. So 2 minutes.
So I'm going to take
58 minutes.
Excellent. I'll take 2 minutes to wrap up. So let's just jump down, just finish this off on climate policy making. We started with this example. I'm just going to rattle through some consequences of some of the things I said. So clearly, IPCC assessments, the IPCC language translates directly into confidence rankings, the sorts of proposal I've been making. And we show in this paper at the bottom that it's difficult to connect to other uncertainty representation. That has a bunch of consequences. Firstly, it has consequences in terms of how you work with uncertainty. There were doubts in the climate literature about whether there was the logic of confidence. I said earlier we provide one. There were doubts whether there was ways or tools to propagate uncertainty downstream in modeling. Essentially, the tools are going to be imprecise probability tools at each level with the lifting rules. There are recommendations for future reporting practices. I'll skip those because I need to take a second on them. And kind of more importantly, given we were talking about decision, it also tells you how the confidence framework should be used in decision. And people don't know what to do with the confidence part of the confidence judgment. The confidence framework tells you what to do with it. It tells you in particular that the confidence part of the confidence judgment, that's something that scientists provide. Which confidence level should be used for decision making? That's a value judgment. That's part of the uncertainty attitude. That's something which isn't epistemic. That's something which isn't on the kind of expert side. That's not to be provided by the people who provide beliefs. That's to be provided by the people who provide the values or desires or tastes, right? So that's something that policymakers should be choosing. Right? Similarly, there was a discussion about the pragmatic vindication of IPCC practices. If you accept the normative credentials of the model I've been setting out, then you're going to consider that as justification of the IPCC practices. And finally, this provides practical recommendations for future use. A very simple, straight out example is you never find people reporting at multiple confidence levels for the same event. But according to the picture we've been proposing, is something you would want, because if you have policymakers who need different confidence levels because they're taking different decisions of different levels of importance, they're going to want to know what judgments they can hold at different confidence. Okay. Hopefully that wraps up at precisely an hour. So what I've tried to do is I've tried to give a kind of glimpse of some of the issues that come out in trying to think about how policy decisions should be made in the face of uncertainty. I've done so by trying to propose and defend a model of confidence and beliefs and a story about how decision making should be made, which is based on this maxim. And we've shown that it has some attractive theoretic properties and supports the belief value separation. Thank you.